the Mars 2020 Deputy Project Manager at JPL, joining us virtually. Ken Williford, Mars 2020 scientist at Blue Marble Space Institute, and Briony Horgan, Mars 2020 scientist at Purdue University. And I'll now turn it over to our panelists.
All right. Good morning, everyone. I'm Steve Lee. I'm talking to you from the Rover Operations Center at NASA's Jet Propulsion Lab in Pasadena, California. And we are preparing for today's operations of Perseverance. Perseverance is approaching 5 years of exploration on Mars. We landed in an area called Jezero crater and have spent much of that time exploring the interior of the crater. And you will hear a little about that from Ken. We have since left the interior of the crater and are now on the crater rim. By the way, are we showing the images?
Mhm.
Okay, great. Because I can't actually see the images. That's right. We'll keep going. So we are currently exploring on the rim and some fascinating terrain ahead that Briony will tell us about. In terms of the rover itself, Perseverance is really in excellent shape. All the systems on board are operational and performing very, very well. All the redundant systems on board are available still, and the rover is capable of supporting this mission for many, many years to come. Okay, now we can see. There we go. Very good. So the images you'll see, the previous one, Brian, you'll show the previous one. This is a zoom in. If one would go ahead to the zoom in a little bit. There we go. This is a zoom in looking more or less north from in an area that we've been exploring and have traversed down to the south. And if you look closely, you can actually see the rover tracks across the valley there approaching its current location where we looked back and took this image. In terms of the rover health, as I said, it's an excellent health. We know that we do trending on an ongoing basis, but we recently did a systematic, very comprehensive evaluation of all the engineering systems on board for mobility, for sampling, for general operations, and concluded that the rover is going to be able to support this mission for many, many years to come. And I should mention this particular selfie is taken at a target known as Chiava Falls, and it is absolutely my favorite selfie of many selfies of the mission. Not only is it a beautiful selfie, but as many of you may recall from a paper this past September, Chiava Falls is a location where we discovered a potential biosignature, which is one of the main reasons for the mission. And we have a sample of this region on board that will be very interesting to look at in more detail one day. The rover health, again, everything looks great. The one area we want to look at more closely is the mobility system, the driving and the wheels. The reason is that originally we tested them to certify them for 20 kilometers of driving total for the mission. Well, we've already exceeded over 40. And so to make sure we can continue operations and continue driving for a long, long way, up to 100 kilometers, we're doing some additional testing. We've successfully completed a rotary actuator life test that has now certified the rotary system to 100 kilometers for driving. And we have similar testing going on for the brakes, and that is going well. And we should finish those early part of next year. Next slide, please. So in terms of how we're using the mobility system, Perseverance really stands on the shoulders of all the previous Mars rovers, most recently Curiosity, and uses much of the same core algorithms, but we've made a lot of upgrades. We've upgraded the onboard software to be able to autonomously drive. We are some of the first autonomously driving vehicles in the solar system, and we have onboard algorithms that have been enhanced further to improve our driving to allow the system to safely figure out the safest path possible and execute that path as quickly as possible. And there's a paper, in fact, coming out that's going to describe in more detail some of those upgrades in our enhanced autonomous navigation system. The video you're about to see here, we can go ahead and hit play, is stitched together from a series of individual frames of our longest ever drive on Mars, 411 meters in an area called Salmon Point, which is where we first reached the western edge of the crater rim. So the images were downloaded and put together so they look like one nice, continuous, smooth image. If you look in the upper left towards the end, you may notice there's actually a couple of dust devils that we caught that sneak through the frame there on the left side. Dust devils are pretty common occurrence on Mars, but it's awesome to catch some in real time during this drive. The last things I'll mention is, we continue to look forward. We are looking to adapt AI technologies to help further improve our drives on Mars, the planning for the drives on Mars. And in fact, JPL recently opened a Rover Operations Center with the goal of continuing to improve our operations, but as well partnering with organizations that are planning their own future operational missions so that we can help infuse our lessons learned, our tools and technology to help them be able to do their operations more successfully and efficiently in the future. And with that, I will turn it over to Ken to talk about some of the findings within the crater rim.
Great, thanks, Steve. And we can just jump to the next slide. So I'll start by introducing you to this lovely green crystal here of a mineral class called olivine. It's a magnesium iron silicate. It's an igneous mineral that forms very high temperatures deep inside the interiors of rocky planets. And it's one of the main reasons we find ourselves in Jezero. That's because, if you hit the next slide, when olivine comes closer to the surface and is exposed to liquid water and dissolved atmospheric carbon dioxide, it transforms in this process called carbonation and produces these mineral products, carbonate and silica. And this process can generate habitable subsurface microenvironments in these water-filled fractures where the chemistry occurs. But it definitely brings together these records of the deep planetary interior with the outermost parts of the planetary system in its atmosphere and the water in between. So very exciting for us scientifically. Next slide. Looking at Jezero crater from orbit, we see the delta there. Sometimes we call it the sedimentary fan, which is what tells us there was once a lake here. And on either side of the delta, we see the margin unit, but right up against the edge or the margin of that ancient lake system in the inner crater rim. We knew prior to landing that the margin unit was at least partly composed of olivine and carbonate from orbital data. But what we didn't know is exactly how it formed. Was it deposited as sediments out of the lake system itself? Or maybe does it represent much older igneous rocks that were then later altered by water and carbon dioxide? Another big question was whether or how it relates to this much larger regional olivine carbonate unit that you see there outside Jezero crater. So next slide. We zoom out now. We see Jezero in the white rectangle. It's really a small feature at this scale on the edge of a much larger, giant, very, very ancient impact crater called Isidis Planitia. And these curving fractures up at the top left of the image, we call Nili Fossae, on the rim of Isidis. And it's that region between Nili Fossae and Jezero where we find the largest known deposit of olivine on the surface of Mars, much of it altered to carbonate. Next slide. So early in our exploration of the margin unit, we investigated the boundary between the sedimentary fan and the margin unit rocks, and we found there an erosional contact, which tells us that the margin unit is older than the fan and the river that deposited it. In other words, the river cut into the margin unit that was existing there before that river system. We find the margin unit outcrops are light-toned, coarse-grained, heavily fractured bedrock slabs that are sometimes layered. Now, layering we often associate with sedimentary rocks, but igneous rocks can also be layered. So we had to look closer. Next slide. Now looking much closer, using our robotic arm-mounted instruments to take images and mapping compositions of the rocks. The areas on the left there, about the size of your fingernail, on the right, even smaller, size of a grain of rice or two. And here we see the chemistry and mineralogy of the margin unit rocks organized concentrically in sort of a bullseye pattern, often with olivine at the core, carbonate on the rim, and the space in between filled by silica. If you remember that chemical equation early on, it's exactly the sort of relationship we'd expect to see from this carbonation process. So very exciting. Again, likely samples there in the crystalline carbonate and hydrated silica of that early Martian atmospheric CO2 and the water in which the chemistry occurred. Next slide. As we continued our exploration of the margin, we ascended the inner crater rim to higher elevations well above where that lake system would have been operating. In the case of this parking spot, about 60 meters, about 200 feet above the highest estimates for lake level. Okay, so the outcrops look very similar to the lower elevation targets, telling us that the margin unit is continuous from those lower to higher elevations. Large fractured bedrock slabs that are coarse grained, but when we look closer again, next slide, sorry, this area about the size of a postage stamp, we see these beautiful translucent green. I don't know if you in the back you can see this, but if you got close, you could see these beautiful translucent green olivine crystals, many of which have their original sharp crystal faces and appear to be intergrown together. So this looks much more clearly like an igneous rock. And this observation and many others from the margin lead us to conclude that the high margin unit, those high elevation targets, are more representative of the original character of the unit. It should be said that alteration, like I've described here, this carbonation process where water interacts with the rock, obscures the original properties of the rock that allow us to confidently determine whether it's, say, igneous or sedimentary. So all these observations you saw here led to some of the most intense scientific debates on the mission that actually continue. You know, how did these rocks form and how were they altered? But this tells us that the margin unit rocks likely formed as what we call a layered igneous intrusion, and then was later altered by water and atmospheric carbon dioxide. With that alteration, the carbonation transformation of those rocks enhanced at the lower elevations by the lake itself. And so we're so excited about the 3 samples we took of the margin unit and their capacity to bring together for us those scientific records of the deep interior processes of Mars and its outermost parts of its system in the atmosphere and the liquid water between. So I think Briony is going to tell you more about our recent exploration and what's to come for the mission.
Great. Well, thanks, Ken. Yes, I'm excited to tell you about what's been going on very recently with the rover and where we are right now. So go to the next slide. So Steve showed this mosaic. This was taken just a few weeks ago from a place called Haiha up on the rim, looking out to the west beyond Jezero crater. So that very lumpy, craggy terrain you can see in the distance, that is what we call Nili-Planin, is the region beyond Jezero. And this region contains some of the oldest rocks exposed on Mars and some of the oldest intact rocks exposed on any terrestrial planet. So we're very excited to get a glimpse of all these amazing outcrops. If you go to the next slide. So here we're looking up the rim of Jezero crater, as Steve mentioned. You can just barely see the rover tracks, as Steve pointed out up there. So we're looking north up the rim, and the reason that the rim itself is such a great place to explore these ancient terrains is because Jezero crater came in, the impactor came in, created the crater, and in the process of uplifting the rim, uplifted and exposed all of those ancient rocks for us to go drive across and investigate. So it's sort of like going to a road cut on Earth. Same idea. This is, nature's way of letting us looking cross section at all these ancient rocks. And so there's a couple different places we've been on the rim that have been really interesting. On the left there, you can see some layers extending north up the rim. There's kind of light tone materials and some kind of redder stuff below that. Those materials we think correspond to some of the most ancient layers exposed in this part of Mars, perhaps on Mars overall. We think they're potentially older, potentially much older than 4 billion years. And these record the earliest history of Mars in the solar system. And actually, what's really interesting about the rim in general is it's giving us a window into a period of time on Mars we don't know a lot about. The interior of Jezero is telling us all about the time on Mars when there were rivers and lakes on the surface, lots of abundant water. But these rocks actually predate that. They're telling us about the Noachian period, very early time on Mars. And we've seen a lot of evidence that it was a very, very dynamic and kind of violent time. So the layers themselves, very ancient, telling us about how the crust was built up on Mars over time. And the area we just investigated over there on the right, where the rover tracks are, is an area called Vernaden. And so that area is composed of breccia. So breccia is a rock that's created when an impact hits the surface and breaks the rock up into small bits. And that area in particular was notable because it wasn't just breccia, it was mega breccia, which is as cool as it sounds. Because some of the lighter blobs you can see in that area are actually giant blocks, tens of meters in size, sometimes larger, of material that were ejected by an ancient impact and deposited in this location. And those giant rocks are amazing because these are actually themselves probably the oldest rocks we'll see on the mission. They were excavated, and they have a crazy history too. Some of them are actually themselves composed of breccia. So what happened in the history of this rock is that a giant impact came in, broke up this rock, partially melted it. A second impact came in, ejected it, and deposited it in this location. And then then the Jezero impact, a third impact, came in and excavated and uplifted so we can see. So it's giving you a glimpse of just how violent the early solar system was at this time, right? So one of the big questions we have is, what was the surface like during this time, right? Was it habitable? What was it like for for life on Mars and Earth that was trying to get going during this period? So that's been a really interesting window into that whole time period. If you go to the next slide, you can see where we're going next. And actually, this is a region called Lac de Charmes, just off the Jezero rim, right at the base. The rover is currently parked down there in the kind of bottom right in that little arc going into this rough terrain. And this is exciting because it's potentially, it's again, the same ancient rocks that are exposed in the rugged terrain of Neoplanum, but we think they're more intact. They're hopefully just far enough beyond the rim of Jezero that they haven't been as messed up and uplifted and excavated as those rocks we saw. And they're potentially a little bit younger, maybe higher in the section, and they might help us understand the kind of surface processes that were happening on Mars this time. So again, what was it like if you were a microbe living on the surface of Mars more than 4 billion? Okay, if you go to the next slide. So after Lac de Charmes, we'll be at Lac de Charmes for probably most of the next year. It's a really complicated, fascinating region. But we've been putting a lot of work into planning our extended mission, which starts next fall. And here's some of the terrains we'll be visiting in that extended mission. So Gardavari down here at the bottom left, that's actually a really wonderful exposure of the regional olivine unit that Ken mentioned. That'll be our first chance to try to connect the olivine bearing units we've seen inside of Jezero and out to this much, much bigger extensive unit on Mars. Singing Canyon itself, that's another spectacular exposure on the crater rim. It's honestly the best one. It has the biggest, best mega blocks, the most altered materials. It'll be a really excellent chance to try to tie all the data we've collected on the crater rim together. So we're really excited for everything that's coming. You know, Perseverance is going strong, and we're excited to keep making amazing discoveries and contributing to Mars exploration.
All right. Thank you, panelists. We'll now open it up to questions from reporters. Please state your full name and your affiliation for asking your question. For those of us joining online, if you'd like to ask a question, please type your full name and affiliation into the Q&A box, not the chat box, and we will invite you to unmute in the order that questions are received. And if you'd prefer to ask your question without speaking, please type your complete question into the Q&A box as well, and we will ask it on your behalf. So are there any questions from the room?
Hi, Jeff Faust, Station. Big picture question. Given the uncertainty about the next steps in Mars sample return, how, when, even if the samples will be brought back, is that affecting your science planning in any way in terms of where you're going, what samples you might collect in order to preserve the option of bringing those back at some point?
Yeah, it's a great question. So we are continuing the mission as you heard Briony lay out. And in fact, we're just now going through the process, which is kind of a normal process within the NASA planning cycle, to look ahead for 2 more years. That'll take us through most of 2028, and are asking ourselves the question, you know, where should we go? What are the explorations? Obviously, the reason we came to Jezero Crater included explorations on the crater rim, and so there are quite a number of very prime, juicy targets we would love to go explore. You know, I should add, as you've seen from Ken and Kate and Briony's presentations, this is a very capable in situ science rover. We have a tremendous suite of instruments to be able to do very detailed investigations and draw some great conclusions and really bring things into context. We are in a very complicated area on the crater rim, as Briony described, and there's a lot to keep us busy. So we do have a plan that we are finalizing, and we'll be working with our headquarters counterparts to make decisions and finalize that for the next 2.5 years to continue this exploration. We do expect to continue some sampling. We have 6 open sample tubes, unused sample tubes on board. We actually have 2 that we took samples and didn't seal yet, so we have options of maybe replacing them if we're finding that there's even better areas that we want to collect from. We do not have any plans to do things like put down a depot of our tubes on the ground. Now, you know, we will just be hanging onto the tubes, and then we'll just see how things evolve in the years after that. But we certainly have more than enough to keep us busy, and we are not expecting a major perturbation to our science explorations in the next 2.5 years as a result of sample return uncertainty specifically.
Hi, Alex Witsi with Nature. Hi, just to follow up on that, do you have a date by which you anticipate filling those final sample tubes?
We have a general plan for how kind of areas that are of particular interest that we think could be particularly diverse sample sets. And so we have a preliminary plan, which, as you might expect, may well change when we get there. We found that all along, that sometimes we get to a point, a place, and it's much more interesting than we thought at first, and it becomes worthy of a sample. And sometimes vice versa, where there's a place where I'm not sure we found any place where you say, "Oh, it's just like before," but maybe it's not quite as diverse enough to warrant using a tube. So right now we don't have a date where we would say, "Oh, we're going to fill up all the tubes." Certainly not in this kind of a time frame. And like I said, we are adopting a strategy in many cases to fill a tube, and we have the option to not seal it. Most of our tubes are sealed, but we have the option to not seal it, and that gives us a flexibility downstream to replace a sample if there's one that we find would make an even stronger representative of the diversity we are discovering.
Any others from the room? I think we've got a few online.
Right, Kimberly Cartier from EOS Magazine has a question for Dr. Lee. You mentioned that you're looking at integrating AI into rover operations. Can you clarify what kind of AI are you looking into? What role would it play in rover operations?
Yeah, no, that's an awesome question, and it's really an exciting emerging capability, as you might expect, and as you can see behind me, we have a team of people who do operations, both looking at the results coming down from YesterSol, what happened in yesterday's plan, and evaluating that, making sure all the systems behaved the way on board, the way we expected them to. Long-term trending, that's one area that can be ripe to have AI help us understand, are there trends that might be emerging? Is there a faster way to do that evaluation? And then we have another room in this building with folks who do the uplink planning, look at what we're going to do in today's plan or the next couple of days plan. And in that area, AI can help as well. If you train those AI algorithms and capabilities, they're able to come up with preliminary plans that can potentially be run on Mars, but we still are at the stage where we want to make sure to do that very carefully because we still want the human to make sure that there isn't anything that is planned that could in some way put the rover at risk. So we still have a lot of human eyes to make sure any plans that are developed are going to make sense and are safe. And we do this with the humans too. We run simulations of our sequences, command sequences before we send them up, just to make sure there's nothing that'll happen that would be unexpected. So I would expect we'll do the same with AI. But it's really exciting to see the kind of capabilities that are emerging and how we might be able to adapt those. And I think you'll see in the coming months, we'll probably have more announcements about some of the results that we're starting to get from adopting this great new technology.
We'll do a follow-up question from Kim. Mars rovers have a reputation for surviving far longer than expected. Presuming that the rover remains in good health, how long can we expect it to continue its operations?
Yes, yeah. Like I said earlier, this rover is in excellent health. It's really in particularly excellent health, if I may brag a little bit. We really are tracking very well with the systems, and so I don't have a date to say, oh yeah, we had lasted at least this long. Look at Curiosity. Curiosity is now coming up on let's see, over 13 years of operations and still going strong. In the long run, we're talking many, many years from now, the onboard power system, the RTG system, it does take advantage of radioactive decay of onboard plutonium, and that ends up becoming a limiting factor. What that ends up meaning is it takes longer to read. It's kind of like charging your cell phone overnight. If you don't have as strong of a link into the AC power, it might take longer to recharge the battery, and so you might not be able to last as long during the day. We eventually, a decade or a couple decades from now, be able, we'll start seeing that and have to adjust our appetites in operations. But in terms of the overall systems, everything looks great. I will say in general, yeah, we definitely have a reputation for testing things, or for showing that these rovers and actually most of our space systems last much longer than we had originally planned. And there's a reason for that, which is we, in all of these cases, those who formulate these missions and think through what will be required, at NASA, they determine, oh, we will need the mission to last this long to accomplish all the science objectives. And so we will get a requirement for mission duration. And then in order to, as I mentioned earlier, certify that we, more or less are really highly confident we can meet that mission, we will test individual systems in a life test, and we'll test it much longer than that requirement just to make sure that we have the additional margin to meet that life test, and accounting for the fact that, we're usually only testing one or two of the units. We're not testing, many, so maybe we've happened to get a good one. Well, we'll test it, maybe 2 or 3 times longer than the requirement just to make sure that we can meet that requirement. That naturally builds in margin. And the last thing I should say is we also don't really have any onboard consumables. In a lot of cases, like orbiting spacecraft, they need onboard propellant that they use for, orbit maneuvering, orbit maintenance, that sort of thing periodically. And that can become a life-limiting factor. Perseverance really doesn't have those kind of life-limiting consumable factors. The closest thing is the RTG, as they described.
We have another question online from Stephen Clark, Ars Technica. What made you choose 100 kilometers for mobility certification?
Yeah,
Do you
that's a
have
great.
specific destinations in mind that led you to that number?
Yeah, no, we certainly did. So there was a process about 2 years ago when Mars sample return, as part of the architecture studies, there were concepts for utilizing Perseverance to not just take samples and seal them in the tubes, but actually support a drive to a landed asset and a delivery of the tubes, in which case Perseverance would have to last long enough after completing a compelling science mission to be able to do that mission. So we actually had laid out a traverse path exploring the crater rim, much more of the crater rim than we have so far, and then be able to return to a rendezvous site. So we did estimate of the total mission drive duration to complete that mission, added margin for science exploration, added margin in case we need to rendezvous at a different site. We're big on adding margin too, just to make sure, because this is a great opportunity. And it just turned out to add up to a nice even 100 kilometers.
Any last questions? No more online?
Sort of a follow-up to that. You mentioned testing the mobility systems. I'm curious how the wheels themselves have been holding up, since I recall Curiosity treads started to get torn up after a while.
Yeah, great question. Yeah, so Perseverance's wheels, the actual physical aluminum wheels themselves are in fantastic shape. What you all may know is on Curiosity, after several kilometers of driving, it was noticed that some of the wheels had little punctures in them that have, over the years, grown into deeper punctures and tears. And we went back, did very extensive evaluation, and realized that the terrain that we were driving on was much tougher and more rugged than was expected before we landed and did the original design and testing of the Curiosity wheels. It was much sharper rocks, much harder rocks, etc. And as a result of those lessons from Curiosity, we made changes to the design on Perseverance in order to make the wheels essentially tougher to handle that kind of even tougher terrain if we had encountered that. And that is proving to play out very well. So we have not been observing any punctures and tears in the Perseverance wheels. So they look like they are in great shape. I should mention, in terms of Curiosity, yeah, they still have punctures and tears that they continue to propagate. If you see some of them, yeah, that does, they're quite visible, but the rover just keeps on going. They have not posed an issue. that has been insurmountable. So the team on the Curiosity rover has done a fantastic job in being able to continue to drive and their explorations, even with these wheels that have these features of damage from the terrain.
Any last questions? Okay. Thank you all for coming. Thank you, panelists. That will wrap up this press briefing. Our next event, for those of you hungry for more cool space science, we've got another press briefing about how science is informing the future of space exploration on the moon and Mars at 11 a.m. here in this same room. And then join us here again at 1 p.m. For another briefing on the worldwide acceleration of sea level rise. Thank you all.
Jefferson.
Administration just